Formal charge is not actually the charge on anything. Formal charge was made up. It's a way for us to evaluate which Lewis structure is the best if we can draw more than one. It is the only way that we can make a determination as to whether or not the Lewis structure that we have is the more likely one out of a set. The formal definition of what formal charge is the number of valence electrons that that element would normally have under normal conditions if it wasn't bonded, minus the quantity of the total non-bonding electrons that are around it, plus 1/2 of the bonding electrons that it's sharing with something else. An easier way to express this is in this Lewis structure for CO2. I have this oxygen atom, which normally in group 16 would have 6 valence electrons. If I follow this equation, I subtract away the number of non-bonding electrons, which in this Lewis structure is 1, 2, 3, 4. Then I cut any bonds that I have in half, because at any given time, oxygen has half of them and carbon has half of them. So at any given time, oxygen only possesses 2 of those electrons, even though they're being shared, and its formal charge ends up being a 0 in this Lewis structure. However, let's look at the oxygen that's in this Lewis structure over here. Cutting this bond in half. I can even start to do this visually, because if I look at this oxygen atom, how many electrons should oxygen have? 6. How many does it essentially have in this picture that I boxed out? 7. So its formal charge is -1. The best Lewis structure is going to be the one that has the lowest amount of formal charge. If we have alternate Lewis structures that produce formal charge somewhere unnecessarily, it's probably not an accurate depiction of what the molecule is actually doing. Furthermore, if I absolutely have to assign formal charge to atoms, sometimes it's inevitable that a Lewis structure will have formal charge. Negative formal charge should be assigned to oxygen or to elements such as oxygen, fluorine, or even chlorine that are more electronegative. If it's necessary to assign positive formal charge should be assigned to atoms that are more electropositive, which means obviously atoms that are not as electronegative as some of the top elements near the top right corner of the periodic table. Okay, so a good Lewis structure ideally has 0 formal charge, but if necessary, negative formal charge is going to show up on the more electronegative element, and positive charge, if it needs to show up, is going to show up on the least electronegative element. The best Lewis structure is the one that has the lowest amount of formal charge. So if I look at these 3 different Lewis structures, the formal charge has already been calculated for us. And if I look here, I have a lot of negative formal charge on this nitrogen here, and I have a positive formal charge on an oxygen. That's a really bad situation. So that's probably not one of the best Lewis structures. Over here, I have a negative formal charge on my nitrogen. It's a little bit better, but ideally, that negative formal charge should be on my most electronegative element. So this third one is the best Lewis structure because inevitably it has to have some formal charge, and it's better to have that formal charge on the more electronegative element. So in this example, I'd like you to draw 2 valid Lewis structures for the compound NaCl. The hint is that the electronegativity of nitrogen is less than that of chlorine and less than that of oxygen. And then use formal charge to determine which Lewis structure is the most stable one. Take a moment, try that, and we'll go over the answer. So just a review from last year, we're actually getting on to the new topic, which is resonance, right? Resonance means the 2 Lewis structures can resonate between each other. We show that with two sets of brackets and a double-sided arrow to show that both of these are valid Lewis structures, but which one is the one that's more likely to predominate? Well, if I look here, I need to start calculating my formal charges around these atoms. And if I do that, all of my formal charges on the left side are 0. I have a -1 formal charge here and a +1 formal charge here. A +1 formal charge on a chlorine atom is pretty bad because chlorine is still fairly electronegative. So obviously this other Lewis structure on the side here is the correct one. Nitrogen, because it is the least electronegative, is the element that should be in the middle. Usually you're going to have your more electronegative elements on the outside. Resonance structures are a way of describing delocalized electrons. And what are delocalized electrons? Well, if there is the possibility that you can draw multiple Lewis structures within a given molecule, it means that the electrons are constantly moving back and forth, back and forth. And how does that happen? Well, we're going to get to a topic of orbital overlap. We're going to talk about sigma bonds and pi bonds. But anytime that you have a double bond that can be moved back and forth within a resonance structure, that's showing that those electrons have kind of like a little tunnel that they can move back and forth and back and forth and back and forth. And they actually cause the Lewis structures to blend together to give you an overall picture of the molecule itself. So it's a situation where we can't just use one Lewis structure. We have more than one good Lewis structure to show the overall resonance structures. So in a resonance structure such as ozone, there's two different ways that we can draw ozone. We can draw it the way that we had before with the double bonds on the left, or we can have the double bond on the right side. And like I said, that double bond can keep moving back and forth and back and forth. Well, that causes the bond character between the oxygen atoms to become a blend. It's impossible for one side of the molecule to have a double bond at any given time. It's actually more of a 1.5 bond. So the overall bond length of those two oxygen atoms becomes halfway in between a single and a double bond. So really a resonance structure causes a mix of the properties of the two types of bonds. Right? Just like you mix together blue and yellow, you get green. If I have two valid resonance structures, that double bond for ozone can hop on either side. It doesn't exist on one side versus the other. It's moving back and forth so quickly that to us, it appears to be more of a 1.5 bond on each side. A 1.5 bond would have a bond length that's kind of halfway in between a single and a double bond. It would also have a strength that is halfway in between a single and a double bond. So it'd be stronger than a single bond, but not quite as strong as a double bond on both sides. So really, not one of them isn't more true than the other. It's more of a blend of both. Okay? We're going to get to this topic when we talk about pi bonding and sigma bonding. But the reason why resonance works is because we have extra p orbitals, and those p orbitals that are not participating in a bond allow those electrons to move, almost like there's a little tunnel for it to move throughout the molecule. So when you see a double bond moving back and forth, it's because of those electrons being delocalized and shared between those two different sides of the molecule. There's a very common Lewis structure that you'll see of a molecule called benzene, and it's oriented in a ring of carbon atoms that have double bonds, and you have hydrogens coming off, and you can see those double bonds can almost move in a little circle around the benzene ring. And those little electrons can move around, and they don't really get held onto one carbon atom. They almost form a perfect circle of movement of electrons throughout the molecule. Benzene C6H6 is a very common example of resonance because those electrons can just keep moving, and those carbon atoms do not have a bond length or a bond strength of a single or a double bond. It's more of a 1.5 bond character. All right. Moving forward, our next topic is going to be exceptions to the octet rule, and we'll cover that in greater detail in your next mini lecture.